Okay, welcome back in my living room this time. Today and also tomorrow and the day after tomorrow we will do the core of the course. That's in fact the adaptive networks. Last week we found already many examples of non-adaptive networks, but now we move to the adaptive case where the networks not only have internal dynamics for the states, but also the structure has dynamics. So that's the topic of today and tomorrow. And tomorrow you will have the first assignment in it, and on Thursday the second one. Today there is still a bit intermediate type of assignment. You can see adaptive network models as belonging to the area of machine learning. Some of you, like the AI people, may have seen already some things in machine learning. But machine learning is just a form of adaptivity. And machine learning is learning as the machine is doing. And if we design adaptive network models and we simulate them on our machines, then it's just machine learning. But the difference is that this is, say, nature-based or nature-inspired machine learning, because I'm focusing on adaptation principles that come from nature, from sciences that study nature. Well, machine learning as topic in general studies artificial types of learning mechanisms. So that's one difference, but I will point at more differences later on. So the idea is that in many cases in the real world, the networks that we can consider are adaptive. You can learn, so therefore mental networks will change over time. You can have memory. It's also a form of changing of your network. But also, of course, social networks are usually quite dynamic. Relationships will become stronger or weaker, or will even completely be removed or restarted. So also in many domains, adaptation has even multiple orders. And that means that the adaptation itself also adapts to the circumstances. For example, for the mental situation, in some cases it's not so good if you learn. It's better to keep what you have, to have a high extent of persistence of what you have learned and not to change that. But there are also cases, like in crisis situations or even in weaker situations, that it's very important to be able to change. So then these circumstances, whether or not it is a kind of normal situation or a kind of more crisis-like situation, it makes whether or not you want to have the adaptation. And that is a form of second-order adaptation. We will discuss that also. So let's first start with maybe the most well-known form of adaptation from the empirical side. That's Hebbian learning. Hebb has formulated it already in 1949 in his famous book. Like this: if there is cell A and the axon is near enough to excite some cell B, and is also taking part in firing it repeatedly, then there is some growth process, so that the connection becomes stronger in this case. In the literature, there are more often used more simplified variants, like what fires together, wires together, or neurons that fire together, wire together. So if they both are active at the same time, their connection will become stronger. That's the idea. Although Hebb formulated it a little bit more careful than this. So that's the first adaptation principle. Still, for those of you who know machine learning, this is in fact a machine learning method formulated as a principle. So I have in this lecture, I have 10 of them. So normally in a machine learning course, you may have multiple methods, but we have 10 methods in one lecture now even. So that goes a bit fast. And I will later show that how we model them, it makes it even easy to really let them work. So another one is not relating to connections. So this Hebbian learning typically is relating to connections in a network. And many of the known adaptation principles have that relation to network connections. But there is also the possibility to have it connected to other characteristics of the network. The general thing is always that it relates to some aspect, some part of the characteristics, some characteristics of the network structure. And you remember we had the network structure, we have the connectivity, we have aggregation, and we have timing. And for all three of these types of characteristics, indeed, we can have adaptation principles. So this one, the enhanced excitability adaptation principle, like formulated in this paper of Chandra and Parkay, indicates that there are also neuron characteristics that change over time. And in this case, the excitability. Well, you already have seen in more than one assignment the importance of the threshold parameter in the logistic function that indeed can model such an excitability. So if the threshold is low, the excitability is high. If the threshold is high, then the excitability is low. Just direct connection between the two concepts. So that can be used, if we make that dynamic, the threshold parameter tau, then we can model this. So I first discuss the principles as they are just described in the empirical literature. And later I will show how we can model them. So from the social science, you have also some principles like the bonding by homophily adaptation principle is also very well known. It's formulated often like birds of a feather flock together. That means if you are more and more similar, then you are more attracted to increase your connection. If you are less similar, it's the opposite, then you are more weakening your connection. There is another one from social science, that's the more becomes more adaptation principle. Persons with more connections attract also more connections. There are different variants or different formulations of this. Someone calls it the rich become richer. There is also the name Matthew principle, Matthew effect, also sometimes used, and there's also the name preferential attachment. But I prefer this name because it's more direct and more clear, I hope at least. So that's another principle from social science. Also about, all these are about connections. There is also a third one that has some and people know, some people know about that. That's the interaction connects adaptation principle. That means that the more correct interaction you have with somebody, the stronger you will become connected. So people sometimes apply this, like they see somebody, they feel maybe I want to be connected to that person. They try to organize things so that you just have projects together with that person or other types of activities so that you see the person often. And then maybe you will indeed, according to this principle, have stronger connection. So that's how that could work. So these are, the previous ones are all first order principles. But there are also second order adaptation principles, as I already mentioned. There is adaptation of adaptation. And one very famous is this one. The exposure accelerates adaptation speed. Adaptation principle. That says in a very short formulation in this paper of Robinson and others, adaptation accelerates, so the adaptation becomes faster with increasing stimulus exposure. So if there is a stimulus coming in, then you automatically open yourself to faster adaptation. That really fits to the idea I just mentioned, like the circumstances make whether or not you have adaptation and to what extent. So this is a formulation of that, which this acceleration ID. But related is the exposure modulate persistence. So I already mentioned that persistence can be important to keep it in certain cases, but maybe in different circumstances you want to have it less. So that's this principle actually. And this is also an interesting principle. the stress blocks adaptation principle. This is at the basis of many disorders where people get in some locked situation and they cannot get out anymore. That says that if you have some stress related condition, and especially the with long duration stress, like chronic situations, then this slows down or even blocks your adaptation capability. That means that if you are in certain situations that you should need to adapt to get well, then this works against you because the stress blocks you to change. And that makes it difficult to get out of such a situation. Kasia describes that you really need some extra impulse to have for a certain time lower stress levels to get this adaptation working again. And then you can get out. That's the way he points out. So this is a very important principle related to many types of disorders, both mental and physical even. So from social science, there are not so many adaptation principles for the second order case available. There are very few. There is some work of Kathleen Carley. She's addressing what she calls inhibiting adaptation. So her idea is that if you want to look at terrorist networks, and their viability depends on that they are very adaptive. They can change many things all the time, and that makes them viable. But if you are able to inhibit that adaptation in these networks, then you may really damage them in a certain way. So, but that's not, there is only very few even from her side on that. You can have, this could be an area that can be developed further, much further, even also in the way that we address things. So there is also an option for adaptive bonding. So based on homophily, I said that depends on how similar you are. But if you already have many relationships, there's very strong connections, maybe you are not waiting and not open for new connections, so that those types of circumstances may also affect your adaptivity for the bonding. So then you can have adaptive bonding. That means that there is bonding only depending on the circumstances. Chapter 6, which I will discuss tomorrow, shows an example of that. But even in the literature, I was not able to find any good reference. Now there is a reference, my own paper on this, but I didn't see any reference from other people. So what I did is to check in the literature, I used Google Scholar and I searched on adaptation. There were, in 1.5 years ago, there were 4 million hits. And I did it recently again, and now it's 4.7, so it increased a bit. Then I tried second order adaptation, then it was 360, and now 426, so that increases a little bit. But now the third order, it was only 14, and now 22, and for this 22, even half of it is our own papers. And fourth order adaptation, was 3, and now it's 9, but these, I think these are almost all our own papers. So it decreases very fast. So the first 2 levels are a bit okay. There are still many research can be found. The higher ones is a bit complicated. So it doesn't mean that it has no role or that it does not exist, but researchers did not publish about it at least. So if you put this in a graph, then if you take a logarithmic scale, then it's still like this. But if you take a double logarithmic scale here, then it becomes a straight line. So that means it goes down very fast in effect. So what are examples of order higher than 2? There is at least one exception, what I can indicate, which is in chapter 7 of the book. It's about evolutionary processes. So then you can have a next adaptation that's often an adaptation of a previous adaptation during evolution. I will discuss that perhaps tomorrow and maybe on Thursday. the example goes through about discussed, but I will not go into detail now. So let's now think about how to model these types of adaptation things. First, I will briefly show how usually that's done. Usually you have a nice network model, which is a kind of declarative description with relations and functions between things. And then they add just some numerical model, and which is not a network model. And that can be, usually it's just an algorithm description or even program code. So it's completely different style of modeling. And then you make interactions between the two. I do it for 2 connection weights in this case, and this is adaptive connections. And then all these connections are needed as the interaction between the two, but they are not even connections because this is not a network. So therefore you don't have connections. This is just interaction in the processing that you have to program. So that's usually done, and people that know, again, these machine learning things, they know about this, how these things happen, but they not usually do not use the base as a network model. So that's not what we want. We want to have a different approach, and that's approach that I will discuss today in some detail. So this is what the situation usually is. But this is not a neat, transparent, declarative network model description, and that's what we finally want. So let's look then what we aim for, and I will show it now only to see an idea of the picture. Then this is a network model, and this is the connections. So now I do it even for all 7 connections here. So it should have been much more complex in the previous hybrid situation. But now it's already even a bit, yeah, you can really understand a little bit that it's not too complex, although I will not explain it now. I will explain it during the lesson, the lecture today. So let's consider the concept of self-modeling network, or a network which has a self-model. That concept may need some explanation, and as you know, I always prefer to explain things by metaphor, like pictures or movies even. So the pictures are here. This time the one good point of metaphors is that they give images in your brain, and images are a very good support for memory. So that's one good reason to use often pictures. Even if the pictures are not completely related, still you can use them as a kind of remembering. So this is a picture of actually of one of my son's Instagram sites, where they address streetwear fashion trends. But anyway, this is, you see that this part is in some sense a model. It models the whole picture. And because there is, you see that the girl even tries to do her best to have a good correspondence. The guy is a bit less motivated maybe, but anyway, it has some similarity. So that's the idea of a self-model. So this is a self-model of the whole picture. You could say it like that. But of course, this is not a good self-model at all, because they do not even look the same, and maybe they are even 30 years older if it's not more. So it's not a really sincere self-model, but anyway, you can see the idea. So therefore we just drop it here. This one is another case. You also have a self-model here. There is one other issue here. This looks quite natural and detailed, but the strange thing here is that what is in the self-model is not in the picture anymore. So you had a picture, you made a self-model of it, but then you destroyed the part of the picture where the self-model is from. That's also not so perfect. So let's also address this one. So let's consider another one. This looks a bit better. You see, this is some head here, and it's still here too, and the head is still there. So that makes that this is a self-model. But in this case, it's a first order self-model because we have more. You can say, yeah, there is this self-model has this part of the picture, but this part of the picture is not in the self-model as a self-model. So then you should actually do something like this. That's also there. Yeah, but you see already, then it goes on forever. And then that's what you call infinite regress. So that's, if you want to have everything in your self-model, what is in the actual picture after adding the self-model, then you come in infinite regress. So that's, well, something also to take into account. This is another example. You can see that it goes deep there, but yeah, so will it ever, it can never be infinite, because you always have the level of pixels. You cannot go into pixels. So let's consider the idea of self-models to design adaptive networks. So we want to take this picture in picture and self-models in pictures as a kind of metaphor to do something similar in networks. So let's see how that goes. So you add a picture of the network within the network. So I will show it first with yet another picture. This is a picture of Douglas Hofstadter's book. And here's the one here who's smiling at you. They are sitting on each other's laps and they don't fall. At least that's what they wrote. And, but it's just an arbitrary picture. So how to make this into a self-modeling picture? Well, it's not so difficult. You make a smaller copy of it, and then you place it in the picture. So you think that's okay. You see what's here is still there, but not totally, because there is still some part here that's not on the picture anymore. So therefore, you always have this problem if you put it inside the picture. But of course, you can also do it like this. Then you should only say, yeah, but now the new frame of the new picture is like this shape. It's not anymore one rectangle, but just shaped like this. Well, that's already a solution for that, because now you have everything that's here is still there. So then we have some possibility to think about the networks. Let's take the takeaway points of this exploration of this picture metaphor. So we take into account the faithfulness of the self-model. The self-model should be a true copy of the original. That was not in the first one. This one was not so good, you remember. So this one. There should be a persistence of the base picture. The self-model should not destroy, hide, or change part of the unit. So this is not a good example, therefore, for this criterion. And we have, and also for that one, and we have this incompleteness for practical cases. So to avoid infinite regress, we will have to accept that a self-modeling picture will always have parts not covered by a self-model. But there is also, for non-practical cases, a form of completeness possible. If you are a mathematician or a magician, then you can have, as a mathematician, a mathematical infinite regress construction. It's just an algebraic construction you can do. And maybe some people think these are the same, but they are not. I'm just one of them. But a perfect magical illusion can also be done something like this, but you see that I'm not a good magician here, but a magician could do this better, that you have kind of ongoing in-zooming all the time. But those are not practical. So for the networks, we need the practical option, and then we have to accept that we have incompleteness. So that's what we already learned. So how can a network model itself? Yeah, by adding a self-model to it, like we did for the picture. In this case, a self-model is a subnetwork with states representing a network structure. Like the network, how it is, it's in its body, you can say, that's the network structure. They are represented by these network structure characteristics, and a self-model is just a picture of that in terms of the states. You have states to represent them. That's the first step that we make. Then we have different possibility. You can have a self-model for connectivity characteristics, for aggregation characteristics, or for timing characteristics. Let's look at an example. For example, you can make a self-model of your connection weight, this one, this omega, and combination function parameter, this one, a threshold parameter, and speed factor, this. You can just make some copy of these network characteristics, and you copy them into states, new states that you add to your network. This one is a W state, this one is a T state, and this is an H state. These are states with their values represent these parameters. So these are called self-model states. And this is in fact a kind of mapping of parameters to variables, which you always should do when you do some adaptive modeling. But we do it in the context of networks, and these parameters are just the network characteristics. That makes it very special. So suppose this base network is there, then we add, we consider all these connection weights, for example, and then we add these W states for each of them. That's the previous example that I give is just this one. So you add, and to make it a bit transparent, you can do it in a kind of 3D illusion. It's just a second plane. This is a bit semi-transparent, and these are just parallelogram shapes and ovals. That's how you create a little bit of a 3D illusion. So this is a plane at a higher level, a level above this base plane. So these are the self-model state, and these relations are the reference relation. These relations are not the connections that are specified in the model. They are just what they mean. So that's in that sense, it's just for not for the processing of the model, but just to understand. So that's the first step. You have some self-models added to your networks by adding some states for the adaptive characteristics. And if this self-model is dynamic, then automatically the characteristics become dynamics. So therefore they become adaptive. Each self-model state also needs new network characteristics. So the states should not be isolated. They should have connections to the existing parts of the network. It should have incoming connections that define the causal impacts on it. It has an outgoing connection to effectuate its effects. And it has aggregation to specify the principle in more detail, a combination function. It has a speed factor, and that's in this case the learning rate or the adaptation speed. So that's also needed for self-model. So let's consider now the Hebbian learning adaptation principle, and now check how we model it. This is a very simple base network. We add the self-model state. We make connections toward it, and that is because we want to model neurons that wire together. Well, to fire together, you need to know at what time these are active at the same time. So therefore you need input for this state for both sides. That explains already for this principle that you need these incoming connections. And then, of course, you need an outgoing connection to the Y itself. That's how it's indicated that this value is used for the connection weight here. So that's how it is modeled. So the pointing of this arrow points where it's used, this value. So that's the wire together part, you can say. So that's the connectivity of the self-model. But of course, the self-model also needs aggregation and timing, as I already mentioned. So that's the next step. So it's the connectivity. It is the connectivity of a connectivity self-model, I should say, because the W represent connectivity of the base model. But what is shown here, it's also the connectivity of that model. So therefore it's a connectivity self-model for that connection, and it's the connectivity of it. But now we also have to do the aggregation. So that means that we need some combination function formulating this principle in more detail. And this is a principle that's very often used. It's also in the library. And it works like this. This part that models neurons that fire together. If both are high, this is the activations of the two states that are connected. If they both are high, then the product will also be high. If one of them is low, like almost zero, then the product is also very low. So that models the firing together part. And then the wiring together part means that it's added to the current value. The W represents here the connection weight that you already have. And then it's added to it. This is only a factor for the normalization that it stays within the 0-1 interval. And this mu is a persistence factor. And it means that if mu is 1, it's fully persistent. You keep everything you learned. But if there is a little bit less persistence, like if mu is 0.9, then you lose 10% of your W every time unit. So that's more realistic in most cases. So that's already how you can model such a thing. So we model it by that picture in the previous slide. This one is the connectivity plus this combination function. And then you model a complete learning method, you can say, because now you can just use it as a learning method. And of course, we also need the timing. The timing, that's very simple. We just set some adaptation speed, some speed factor for the W, and that's then the learning rate. So that's all how you can specify a learning method. In this case, the Hebbian learning method. So let's check another one, the enhanced excitability adaptation principle. Then you need a state representing the threshold value for this state. And that's this one. And it needs, for example, input from the, say, this exposure, the stimulus exposure, if it comes from this side, for example. But it can also be other things. And it has effect on Y in the sense that this value is used for the threshold. So now it's not a fixed threshold in the matrix, but it's the threshold defined by this value of this state, which is every time different. Therefore, it's adaptive. So that's the aggregation self-model, but still only the connectivity of it, of course. It's only the connectivity picture here. It's one form. There are more forms of aggregation self-models. And then we can use for the aggregation, in this case, just logistic or Euclidean functions. So sometimes you can just use the standard functions for that. And then you can also have this adaptation speed as just a speed factor. So it's also quite simple. So this is another one, timing adaptation principle. Then you have state H, representing the speed factor for this state. And then for example, in some case, you can model it like this is a kind of context factor, like how much time do you have available. If you have not much time, you will not respond very fast on your email or on social media. If you have much time, you will respond faster. So that's how it can connect to this speed. So this is then also the downward connection here, and this is then the picture of the timing self-model. By the way, this can be applicable for mental, but also to social network models. It can be applicable in many cases, even as second-order principle. I will show it later. So again, you can have the more standard functions here. I go further to one other form, is the combination function choice. At the end of today's lecture, I will show a simulation of that as well. So that means that you have these are the the combination function weights that you specify usually in this matrix MCFW. And so the first, the second, and the third function. Usually you specify only one and then the rest is 0. But you can also have all of them some value. And you can have these values dynamic. And that's actually what this adaptation principle does. So these values, they may depend on certain context factors. And then depending on that, you will use for this Y more of this or more of that or more of that, because the weights are changing all the time. So that's also such a principle. And we will see later an application of that. And also here you can use standard functions again to specify it in more detail. So one thing that I want to point here is that these self-models, maybe you can see they are fantasy things or artificial modeling constructs, but there is actually really a relation to the world of these things. For example, if you do the connection weight, like Hebbian learning, there is in the real world a synapse configuration in the brain. So that you change that configuration and then that's the learning. And also like this excitability adaptation, there is in an internal configuration of your neuron. And that defines the excitability. So if that configuration changes, then the excitability changes. So also in these other things like the stress situation, there are always, say, physical things that are underlying these concepts. They are not just fantasy. Okay, now the next step is to the social network area, the bonding by homophily adaptation principle. This picture is actually just the same as the picture of Hebbian learning, but now it applies to the social situation. In this case, we have this principle, birds of a feather. Then we need to see from these states in how far they are the same. So the more similar these states are, for example, their opinions, the more similar the opinions are, the more you want to change your connection in the positive direction. So therefore you need input from these states. Therefore these arrows are there. And then, of course, as always, we have the downward pink arrow that makes that this value is actually used as the connection weight for that connection. So this is exactly the same picture as Hebbian learning, but this is not the case for the aggregation, because this is only connectivity. So this birds of a feather flock together totally. So that's the connectivity of the self model. Now we have the aggregation, and also here we use a special function, which also is in the library, and even more variants as well. Like in Hebbian learning also, there are more variants, and they are described for Hebbian learning in chapter 14, and for this case in chapter 13, the different variants. So this is also an option for a function that can be used for this case. I will explain in a moment how you can see this formula. Then of course you need the timing, you need speed factor also. In this case, the adaptation speed. So let me show how this formula works. You have to model birds of a feather. That means a high extent of similarity. That means that the difference between the two values of the opinions, for example, of the persons should not be big. So we assume that there is some tipping point, tau, that if you consider they are very much similar, if it's below this tipping point, for example, this tau is 0.2 or 0.15 or something like that. So that this is the criterion that they are birds of a feather. And you can rewrite this like this: the tau minus that is positive, and that's exactly this part. So that represents that this is positive, and then indeed this part becomes positive as a whole, and it is added. So that strengthens your connection because something positive is added to it. So that's the flock together part. So this is how it works. If it's bigger than tau, higher than tau, then this number becomes negative. So then it subtracts. So therefore your connection will become bigger. So that's the rationale behind this formula to model this bonding by homophily principle. And as said, there are different variants in the library as well. So then there are a few others that I want to briefly go over them. That's the triadic closure adaptation principles from the literature, from the social science. If you have, for example, a strong connection with your parents, I should do it here. If you have a strong connection with your parents and also you have a partner, then sometimes they will meet each other, maybe at birthdays or other cases. And they will start to have also some connection. So therefore, if these two connections are there, then this third connection will also occur. Maybe not as strong as the other ones, but at least some form of it. That's what is called the triadic closure adaptation principle. Notice that now there is no connection from down, there is just a relation to connections. So if these connections, they affect the other connection. And then, of course, we have connections down to make the effect working like normally. So this is again another form of connectivity self-model. Also we have this again, we know it. This becomes more adaptation principle is like this. It has some similarity to the triadic closure maybe, but usually it's not considered in the literature as similar. It's usually just two different areas. So if you have, if someone, this Y has many connections already, then as a person X3, you let your choice whether or not to connect to Y depend on how many connections are already there. So then you have this situation. And you see the picture is almost similar to the triadic closure picture. So let's consider some more. Interaction connects principle. Then you have some interaction states that shows the activity that you have together with somebody that affects your connections. Well, simple. And then you can still make some functions for that. You can just model it like that. So let's now continue for the second order one, and after that we will do the example simulation. So remember this one, we want to go for the second one, the second order self-model. So consider this principle, for example, from Robinson et al. Adaptation, that's modeled by the first order self-model. That's what we already know, that fits there. Accelerates, that's part of the second order self-model, because the adaptation is what's accelerating, and that's modeled by the second order model. And the increasing stimulus exposure is just in the normal base level. The other one from Kasia, for example, high stress levels slow down or block adaptation. The adaptation again is in the first order self-model. The slow down or block is in the second order, like the accelerating here, but now it's the opposite. And the high stress levels are in the base level. So that's how these things can be related to the different levels in your network now. So this is an example then of a second order principle, and that's the exposure accelerates adaptation speed principle. We already have here the normal adaptation, the Hebbian learning principle, for example. Then you adapt the adaptation speed by this here. So the exposure accelerates, so therefore the exposure is used as input for it, and also even the current situation with the W. But then the accelerating is just that this value that's increasing over time, for example, then is used here for the speed of change of this W. So that's the learning rate. So that's, now we have two levels. And tomorrow we will have in the assignment an example of this two-level structure. So that's a timing self-model. Actually, that's the same as the timing self-model we already had for the first order also. But now it's used to make it a second order timing self-model, because we add it to another first order model. So then another one that's in the same area, then we have the mu. This models the persistence factor mu, this one. And that can be dynamic in this way. And then you have exposure modulates persistence, then you also need exposure as incoming, and you have the effect here. And then you can have some second order aggregation self-model, because the mu is part of the aggregation. And also you can use just standard types of functions. So that's an overview. I have told you and explained to you in a relatively short time at least 10 different learning methods, adaptation methods, and how you can model them. And I don't think in many courses that address learning it happens that fast, but I hope you can learn it in the next today and the next days how it really works, and indeed how you can do it yourself. But let me illustrate it now by just one example that is also showing the simulation. So suppose we have a manager that starts to work in an organization, and she adapts over time to some experiences that she has in the organization. She represents the opinions of her group. members, and she did it in the first time period like just a scaled sum function that often is used for modeling such things in general. But later on, she tries to avoid the more extreme opinions and to make a logistic function with a relatively high threshold so that she makes it a bit modest, the opinions. And also her response time fluctuates with her workload. So if she's busy first, in the first period she's very busy, later on she's less busy, and then the response time will be faster. So how can we model this? This is the manager opinion that's based on the group opinions. This is the available time of the manager. This is the disappointment level of the manager. These are the group members. They also have mutual connections. I leave them out of this picture, but they have some contagion mutually as well. But they at least affect the manager opinion. So this is what the base network is. Then we add a self-model for it. That's for aggregation and timing for the combination function used in this state, and also for the speed of this state. And for the speed is this one, and these are the two weights for the two combination functions. One for the, this was the scaled sum, I think, and the other one was the logistic function. So you have two weights now. Normally you choose one function in the role matrix in the table, and the other ones you make 0, or you just leave them empty. But in this case, it's typically a situation where we have two filled. Both of them are non-zero. And over time, the ratio between them changes. So we have these states. This one represents the weight comma 1 for the scaled sum, and this one represents the weight comma 2 for the logistic function. And this one represents the eta, the speed vector, for this state. So this is the model then. We add some extra links to influence these states to have the adaptation really working. And we have, for these three, we all use a normalized scaled sum function as functions. So let's consider the role matrices. So this is an important question. How would you specify in the role matrix that you want to have adaptive characteristics? Normally, the role matrices, they show numbers. That's how we got accustomed to them last week. Now, they will not be all numbers again. Here, there still will be numbers, but some places, there will not be numbers again, like this. And also here, in some places, there will not be numbers again. So like this. So what you write there, you write just the reference to the state that represents that value. So now we have the x12, that's the C1, that represents the value of the weight for this function. And the x13, that's the C2, represents the value for that function. That's the way how they can become dynamic, because these are just dynamic states. And they have their own connections here and their own weights and everything, and speed vectors. So they are just running over time in different values. And the same here. Instead of a value here, you just put an x11 in this case that represents the speed vector for this manager opinion. So the speed vector normally would be 0.05 or whatever. But now it's just changing over time because of this change. So that's how you do it. So it's actually very simple. And we just use the same role matrix format. Yes, you have to add, of course, your additional self-model state. So therefore you have some more states. But then further, the principle is just the same, except that in some places you don't have numbers anymore, but variables that are indicated to other, like the other states that are used for that. That's all. Tomorrow I will show in detail how you copy these matrices in MATLAB, because we have an adaptive template where you can have the adaptive things as well. And then you have to do something with these, but I will explain that tomorrow. So these are the IDs. Then you have role matrices. You just copy them to the adaptive template, like almost like you do it for the non-adaptive ones until now. Then you can simulate it. And then you see, for example, this graph. This is the graph of the base network. And then this graph for the self model. It's good to have two graphs. If you put all these in one graph, it becomes a bit too full, it's a bit crowded. So this is the, let me see, this is the scaled sum is dominant first. And then we have the increasing disappointment over time. And therefore here there is a change in dominant combination function because now the logistic function becomes dominant. And this goes down. So therefore there is a switch here from combination functions over time. And also here you see then that these are the group members. They have some contagion, as you can see. This looks like assignment 3. They just converge to some common value. And the manager opinion first is some kind of average of this group, but after using this logistic function with a higher threshold, she becomes more modest in the opinion, and then even very low, maybe too modest here. So that's why this goes down. Well, and also the available time is just this one. And then we have here the speed. If the available time goes up, then the speed goes up. And then this is also visible here, but then you have to read more carefully also compared to other cases with constant time. So this is just an example of a simulation of such an adaptive network model. Here you see the base network dynamics, and here you see the adaptation dynamics. So that's all what I want to show today. This is the starting point of modeling adaptive networks for the rest of the course more often. So we have dynamics and adaptivity, both are important in real world applications. We can use self-models to do the adaptiveness of networks. We can do it like multi-level self-models to have higher order adaptation, but actually almost nobody does. Even the more normal learning people, they almost never have higher order learning or higher order adaptation. While in the empirical literature, those things, at least for the second order, are described. And tomorrow I will discuss that example in more detail for plasticity and metaplasticity for the mental and neural situation. We have now a portfolio of self-models that can be used as building blocks, because I've explained to you, at least for 10 situations, 10 forms of adaptation, how you can use it, how you can do it. You can just reuse this as building blocks. And then you have a lot of possible applications in different areas that are possible. And remember that the design of such network models is just based on modeling, not on programming or algorithmic specification. And that's all because the software environment takes it from our hands, because that just runs them from matrices, from the role matrices. Okay, so where are we? We are now in week 2. So we start now to think about designing adaptive network models. And you had a first course in that today. Tomorrow I will go in still a bit further detail into it, and you will work on it in assignment 5. Then on Thursday there will be other cases. The evolutionary example I will discuss in some more detail. And also the second order bonding by Humphrey. And you will do your own assignment on bonding yourself, which is actually a sequel on this soap story from assignment 1. Then after that, we will move. So until now, we do designing of network models. And then we will do analysis of network models and their behavior. That starts on Friday with social network analysis. And then we will continue this analysis in the next 4 days, next 3 days, so that in total we do 4 days on it. And then we have also some assignments on them. The 4 assignments from 7 to 10 all are about analysis, but 10, but also 8 is about how you can use empirical data from social media or from other sources to compare to your model and to change your model so that it becomes better fitting to what you are modeling. And you have some automatic methods for it, like parameter tuning that we will discuss on Thursday. So this is the perspective of the course for the coming time. Assignment 4 is actually not very difficult. I saw already in people that were submitting the assignment 3 that some elements are already there. So probably many people will not have difficulty with understanding of these and may already make this assignment in 1 hour time. But if you find it more difficult, maybe you really want to use this assignment to get more understanding of the ideas of these 2 concepts. So that's for today, the assignment. But of course, if you still have questions about assignment 3 or one of the other assignments, you can also post them. So that's all. Are there questions now in general?